Hello everyone, welcome to the extra class or summary session of spread spectrum communication. So today we will be doing some extra bits from spread spectrum communication for an hour-long class. So this will not be a full class but rather an extra class for for discussing topics that will not be covered or might be covered fleetingly in the main 12 weeks of the NPTEL course. So today is a summary session, and also we will be solving some problems related to spread spectrum which we have not done previously. So okay, so we will be doing some problems on spread spectrum. Let's share my screen. So the first problem is that assume we wish to transmit a 56 kbps data stream using spread spectrum. Find the channel bandwidth required to achieve a 56 channel capacity, kbps channel capacity when SNR equal to 0.1, 0.01 and 0.001. Okay, so first we have to find the channel bandwidth that is needed to achieve a particular 56 kbps data rate for SNRs 0.1, 0.01 and 0.001. Okay, so the first extra session for spread spectrum. So the 56 kbps is here. By Shannon's formula, we know that the channel capacity C is equal to bandwidth times log base to 1 plus SNR. So the first problem, the bandwidth will be C by log base to 1 plus SNR. In the first one, for SNR equal to 0.1, the bandwidth is equal to C 56 kbps. So 56 So it should be 430 kilohertz. If you solve this will come to be 430 kilohertz. Next, for SNR equal to 0.01, the bandwidth will be 56 log 2 by log 1.01. So this will be 3.9 megahertz. So as you see, the worse the SNR gets, To maintain the same data rate, you are needing higher and higher bandwidth. So your bandwidth efficiency reduces with SNR. Next, if an ordinary, not spread spectrum system, a reasonable goal for bandwidth efficiency might be 1 Bps per hertz, that is to transmit a dataset of 56 kbps, a bandwidth of 56 kilohertz. In this case, is used. In that case, what is the minimum SNR? So, yeah. Now, bandwidth efficiency. ম্যাম কিছু আমি ইয়ে করছি, ক্লাস নিচ্ছি, ক্লাস নিচ্ছি। So the bandwidth efficiency here, they have demanded bandwidth efficiency to be 1. So log base to 1 plus SNR has to be 1. That means 1 plus SNR has to be 2. So SNR has to be 1. So SNR 1 means your bandwidth efficiency is 1. SNR and bandwidth efficiency are directly related. So SNR has to be 1, or in decibel terms 0 dB. Okay, so now we know that spread spectrum approaches are the frequency hopping spread spectrum and the direct sequence spread spectrum. In direct sequence spread spectrum, the frequency of the in direct sequence spread spectrum, the message is modulated by the code, and the message is modulated by the code, and the spread spectrum code or spreading code changes the message so that it spreads in bandwidth. Whereas in frequency hopping spread spectrum, the frequency of the message signal is changed between discrete hops. So it is changed in steps of discrete hops to get the proper signal, to get the spread spectrum signal. So basically here we are spreading the bandwidth in terms of multiplying with the data, and here we are spreading the bandwidth by changing the frequency. Yeah. So the first example is, what our first question is, what is the minimum number of bits in a pin sequence if we use FHSS with a channel bandwidth of 4 kilohertz and spread spectrum bandwidth of 100 kilohertz. So the spread spectrum bandwidth is 100 kilohertz and each channel is of 4 kilohertz. So how many hops can we accommodate? The channel bandwidth is 4 kilohertz and the spread spectrum spreaded bandwidth is 100 kilohertz. So spreaded bandwidth is 100 kilohertz. So the number of hops we can accommodate is 100 kilohertz by 4 kilohertz, so 25. So there will be 25 number of hops. So there will be 25 possible frequencies. So to hop between 25 frequencies, the number of bits in spreading code will be log 25 to the base of 2, which comes out to be 4.64. So 4.64 bits, of course, we cannot have, so we will have 5 bits. So now spreading code should be at least 5 bits long. Okay. An FHSS system uses a 4-bit PN sequence. If the bitrate of the PN is 64 bps, what is the total number of hops? So here, the next question, let's read it again. So FHSS system uses a 4-bit PN sequence and bitrate is 64 bits per second. So what is the possible number of hops? The number of hops does not depend on the bit rate, it depends on the number of bits, because 4-bit PN sequence implies 2 to the power 4 equal to 16 spreading codes. Now 16 spreading codes means so 3 to the power 4 equal to 16 spreading codes. Thus, number of hops will also be 16. At most 16. It can be less than that, but it will never be more than that. So number of hops is 16. Next, what is the number of finished cycles per time of PN? So if 64 bits are transmitted per second, so how many codes are transmitted? It's basically asking for the code rate. Number of cycles is basically the number of codes. So code rates is 64 bits per second, and each code has 4 bits. 4 bits per code. So 64 by 4 is 8. 8 codes per second. Sorry, 64 by 4 is 16. So 16 codes per second. 16 codes per second. Next, a pseudo-random number generator uses the following formula to create a random series. Ni plus 1 equal to 5 plus 7 ni mod 17 minus 1. So Ni is the current random number. You multiply by 7, add 5, and the remainder, when you divided that result by 17, you subtract 1 from it to get the next number. So that is the rule. So what are the random numbers? So Ni plus 1 is equal to 5 Ni plus 7 mod 17 minus 1. So N1 is 5N0 plus 7 mod 17 minus 1. So mod we can represent by this symbol minus 1. Now n naught is seed. We can assume n naught equal to 0 because we have to assume some value for the seed. So let n naught equal to 0. So n1 will be 7 modulo 17 minus 1. So that will be 7 minus 1. So 6. Next n2. n2 is 5n plus 1 plus 7 modulo 17 minus 1. So 5 6 are 30. 37 modulo 17 minus 1. Now 17 in 2s are 34, so 3 remainder. 3 minus 1, so the next number is 2. Now n3, this will be the last one I will be doing. So n3 will be 5 into 2, 10 plus 7 modulo 17 minus 1. So 10 plus 7 is 17. 17 modulo 17 is 0. 0 minus 1 is minus 1. So the sequence goes like, if you start with 0, 0, 6, 2, minus 1. So of course, if you start with another seed, you might have another value, another chain of values. So if you, so in the next step, minus 1, now put minus 1, you will get 2 modulo 17. So 2 modulo 17 is 2 minus 1, so 1. Next 5 plus 7, 12. 12 modulo 17 minus 1 is 11. So here we see that the period is either too long or we are not getting any period, and the minus 1 itself might not be permissible. So 0 is not a good seed to start. Here you can see that with 1 they have started, and with 1 they have achieved periodicity within 8 hops. So the random numbers will be 11, 13, 10. Now here we have got minus 1. So the random number will be 0, 6, 2. If we stop when we get the first minus negative number, so the random numbers will be 0, 6, 2 by that logic. Okay. Now try this problem. I'll give you 2 minutes. 5 minutes rather. Take 5 minutes, and then we will go back to the next to the solution of this problem. If you want, you can fast forward to 5 minutes and see the solution directly. Okay, so the question states an FHSS system employs a total bandwidth of W is equal to 400 megahertz and an individual channel bandwidth of 100 hertz. What is the minimum number of PN bits required for each frequency hop? So it has a total bandwidth of 400 megahertz and an individual channel bandwidth of 100 hertz. This will enable us to calculate the number of hops. So equal to spread bandwidth, the number of hops will be equal to the spread bandwidth by the individual bandwidth. So the spread bandwidth is 400 mega and the individual bandwidth is 100. So 400 mega or 400 into 10 to the power 6 by 100. So it will be 10 to the power 6. The number of hops will be 10 to the power 6 or 1 million. So there will be 1 million hops. Okay, and what is the minimum number of PN bits? So if there are 1 million hops, the number of bits required will be the log base 2 of 1 million. So number of bits in spreading code is equal to log base 2 10 to the power 6. So it is 6 into log 10 base 2. So log 10 base 2 is 3.32. So 6 into 3.32 is 19.93, which means 20 bits. So 20 bits will be needed in the spreading code. With 20 bits, you can generate 1 million possible hops. Sorry, this will be 4 million, not 1 million. This 4 is not cancelled, so 4 million. So with 4 million, of course, you have to add a so yeah, it will be 6 into log 10. Now log a into b is log a plus log b, so it will be log base to 4. So it will be 19.93 plus 2, which is approximately 22 bits. So it is 22 bits. Okay, so commonly used multiple, so FHSS commonly uses multiple FSK. Multiple FSK uses n equal to 2 to the power L different frequencies to encode digital input L bits at a time. So there are 2 to the power L different frequencies and you do a FSK of that. So the total FSK bandwidth is 2 to the power L into FD, and the total FHSS bandwidth, this is the after spreading after modulation, and the spreading after spread spectrum will be 2 to the power k times that. So so they have the frequency is shifted every TC seconds, where TC is like the hop time and TS seconds is the duration for which the symbol lasts. So a fast FHSS is when TS is greater than TC. If TS is greater than TC, then within one symbol duration, you have multiple frequency shifts. That is a fast FHSS. Whereas in a slow FHSS, the signal elements change within one hop. So you will have multiple adjacent signals which are sharing the same frequency. So that is a slow FHSS. So now this is a problem. So here you can see 19 time slots. Each time slot corresponds to one bit. Now they are transmitted in the following frequencies: F1, F3, F23, F22, F8, F10, like that. So, and therefore there is a frequency PN sequence correspond to this linked to these frequencies. So, what is the PNC period of the PN sequence in terms of the bits in bit sequence? So, what is the period of the PN sequence? So, you see 001, then you get 110, then 011, then you again get 001. So, so you see that the block 0123 is the same as the block 12, 13, 14, 15. So every 58 times it changes bits. So the period PN sequence in terms of bits will be 15. So 15 bits, every 15 bits the PN sequence repeats. So it is 15 bits. The system makes use of form of FSK. What is that FSK? That FSK is MFSK, multiple FSK. Okay. So what is the number of bits per signal element? So here what is the number of bits per signal element? So one signal element is determined by one hop, one frequency. So you see that two, only two frequencies, only two bits are represented by one frequency. So the number of FSK frequency, what a number of bits per signal element is 2. So there will be 2 bits. And what is the number of FSK frequencies? So the number of FSK frequency, as there are 2 bits per signal, so those 2 bits can be in 4 different combinations. So the number of FSK frequencies will be 4. And what is the length of PN sequence per hop? So per hop you have 1. So this is F1, F3 is 1 hop. This change from F1, F3 to F3 is because of the MFSK, not because of the spread spectrum. So this constitutes 1 hop. So 3 bits are there in 1 hop. Okay, so is it a slow or a fast frequency hop? So you see that it takes 2 seconds, like 2 units of time to change the symbol element, but it takes 3 units of time to change the code element. So TC is 3 bits and TS is, so every 3 bits, because PN sequence is 3 bits long, so it takes 3 bits or 3 units of time, because each bit is taking 1 unit of time, so 3 unit of time. It can be second or microsecond. And TS means signal element. So you see this frequency is changing, maybe because of hop, maybe because of this symbol element, it is changing every 2 bits. So TS is 2 bits. So within TC is greater than TS, which means within one symbol element, within one hop, multiple symbols are there. Within one hop, multiple symbols are there, multiple data symbols are fitted. So here 1.5 data symbols are fitted in one hop. So it is more than one. So multiple data symbols present, which makes it a slow FHSS. Okay, so this is a slow FH system. Now, what is the total number of possible carrier frequencies? So, there are two possible ways, there are four possible ways in which the frequency is being altered by the MFSK, and there are this PN sequence has the PN sequence has uh, 3 bits per element, so 2 to the power 3 8. So PN sequence is 3 bits long. Implies number of hops is equal to 2 to the power 3 8. Now MFSK has 2 bits per symbol, so number of modulation frequency is 2 to the power 2, that is 4. So number of, now a combination of one hop and one modulation frequency together will create one unique carrier frequency. So the number of carrier frequency is 8 into 4, all combinations of the number of hops and the number of modulation frequency. So it is 8 into 4, which is 32. So there are 32 possible carrier frequencies. Now we come to DS3. So direct sequence spread spectrum is a form of spread spectrum in which the message is directly modulated with the code chips to generate the spreaded signal. So it is more straightforward. The spread signal is simply the multiplication of the original signal and the spreading code. Okay, we have a digital medium of data rate 10 Mbps how many 64 kbps channels can be carried by this medium if we use DSS with Barker sequence. So the Barker sequence is 11 bits long, so it will increase the bitrate 11 times. So a 64 kbps channel will need 711 into 64, which is 704 kbps of bandwidth. So if it needs 704 kilohertz of bandwidth and the total capacity is 10 mbps, so each channel is consuming 704 kbps after spreading. So 10 mbps by 704 kbps gives 14 channels. So we can accommodate 14 channels. Okay, so the number of bits you have in the in the spreading sequence is the number of times your data rate will get multiplied. Okay, so code division multiplexing. Code division multiplexing is a multiplexing technique that uses spread spectrum. So it will create multiple chips or codes. Then it will assign each chip to one user, and it will multiply the chip with particular chip with that particular user's data only, and thus if it has k chips and the data signal rate is d, so now it will have a kd chips per second transmission. So say c1 code is assigned to user 1, so user 1 wants to send data d1, so d1 into c1. Similarly, d2 into c2, d3 into c3, and d4 into c4. Now all of them are together combined, so each of them say has a rate of d kbps, so it will be d plus d plus d plus d, 4d kbps. Now capacity is needed. So how many users? If you have n users, you will have nd kbps. Now the data representation in CDMA has to be that 0 has to be mapped to -1 and 1 has to be mapped to +1. That is, it has to do a bipolar coding, because 0 might indicate that there is no signal, it is silence. So to avoid confusion between data 0 and silence 0, we do bipolar coding, and then we multiply with the chip, and we will get the final data by adding all the D1, C1, D2, C2s. So we have this particular problem where we have the codes user A and user B has two different codes as shown here. Okay, show the output at receiver A. So the A and B has the codes as follows. So if A has the code -1 +1 -1 +1 -1 +1 -1 +1. So this is one. Another is -1 -1 +1 +1 -1 -1. So if A transmits 1, B transmits 0, that is silence, then channel data will be simply +1 into code of A. So CA. Now this is CA. I am not writing it again. This is CA, the code of A, and this is CA. So simply the code of A will be transmitted. Now if A transmits 0, A transmits 0. Here B does not transmit 0. It transmits nothing. If A transmits 0, then it effectively transmits -1. Whereas B, silence. So B will transmit 0. So the data will be -1 times CA. So minus CA. It will be +1 -1 +1 -1 +1 -1 +1 -1